Congruent triangles don't just help us prove that parts of triangles are congruent, they can actually help us prove other theorems. Before we begin this particular example, we do need another definition. Our definition is equidistant. Can you tell that this word is created by putting two words together, equal and distant? A point is equidistant from two objects if it is the same distance from both objects. So if we look at point P, it happens to be 5.5 centimeters away from point A, and it also happens to be 5.5 centimeters away from point B. So point P is equidistant from points A and B. So with that in mind, I want to take you back to when we were doing constructions. Now if you missed the unit on constructions, don't worry about it. This kind of explains things as we go along. Remember when we constructed perpendicular bisectors and we took a compass and we put the endpoint on one of the points of the segment and we created an arc, and then we turned the compass around, put the point on the other end point, and did another arc. And where those two arcs intersected, we drew a line. And that line we knew was going to be the perpendicular bisector of that segment. So it would create a right angle, and it would also divide the segment into two congruent parts. Okay? So notice here that P, point P, happens to be on the perpendicular bisector. Let's simplify the figures so we're just looking at these things. Now, I'm noticing something here. Right angles are congruent to each other, and because the segment was bisected, we have two congruent segments. And segment PE is congruent to itself by the reflexive property. So if I were to draw in two more segments to finish two triangles, those two triangles would be congruent by side angle side, wouldn't they? That's interesting. And notice that segment AP and BP are then congruent to each other because of the definition of congruent polygons. Now hold on to that thought as we go to our next theorem. This is called the perpendicular bisector theorem. It says that if a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. And what did we just basically prove? We proved that if segment PQ is perpendicular to segment AB, and segment AQ is congruent to segment BQ, then AP is equal to BP. How does this help, you ask? Well, let's do a quick example of how we can use this. Ooh, what is the length of segment RP? I don't know. I see these triangles. It scares me. But if you notice here, angle RMQ is a right angle. That means that segment RM is perpendicular to segment PQ. Also, notice that segments PM and QM are congruent to each other. Oh, that means segment RM is the perpendicular bisector of segment PQ. So that means that point R has to be equidistant from both points P and Q. Or those two lengths are equal to each other. Ho, ho, ho. Now we have an equation that we can solve. We subtract 5x from both sides of the equation. We add 32 to both sides of the equation. We divide both sides of the equation by 2, and we find out that x is equal to 25. But wait! We're not done yet! Because we weren't asked to just find x, we were asked to find the length of segment PR. So we could simply plug that 25 in for x. 7 times 25 minus 32 winds up with 143. So this is one way we can use the perpendicular bisector theorem. Now it's your turn to do a few problems and then watch the next video.